A linear, equations, functions, zeros, and applications. Take a minute. You can pause it. These are our objectives for this section. Equations and solutions. An equation is a statement that two expressions are equal. To solve an equation in one variable is to find all the values of the variable that make the equation true. Each of these numbers is a solution of the equation. The set of all solutions of an equation is its solution set. Some examples of the equations in one variable are seen right here. And what they mean by one variable, you notice each one of these only has X. They don't have a Y involved. Okay. A linear equation in one variable is an equation that can be expressed in the form of mx plus b equals 0, where you notice that we only have X. We don't have Y involved. M and B are real numbers, and M cannot equal 0 if we're going to have a linear equation here, because if M equals 0, then there's no X. Okay. Equivalent equations have the same solution set or equivalent to equations. Okay. So what is it saying? For example, 2x plus 3 equals 5 and x equals 1 are equivalent equations because 1 is the solution of each equation. So what it's saying is when x equals 1 and we plug it into this equation, we get 2 times 1 plus that 3 equals 5. Well, 2 times 1 is 2 plus 3 is 5. So yes, they are equivalent because it does give me a solution of 1 for x and so on. Okay. Equation solving principles. Okay, for any real numbers A, B, and C, the addition principle, if A equals B is true, then that means A plus C equals B plus C. So if A and B are equal, then I can add C to both of them and still get a true statement. That's the addition principle. In the multiplication principle, if A does equal B and they're true, that's a true statement, then I can times C to A and it's still going to equal B times C. So here we go. It says solve this equation when we have 3/4 x minus 1 is equal to 7/5. So what we're going to do is start first. We notice before I get to the next thing I was going to say, we notice that we have a fraction and we got addition and subtraction going on. So what we need to do is find the least common denominator, right? Because if I can find the least common denominator, I can undo this fraction. So I noticed that the denominators have a 4. This one's just seen as over 1, and this one's 5. 5 is prime, so I can say 4 times 5 is 20. So we're going to call it our least common denominator. And that means every term is going to be multiplied by the 20. What happens is I can put a 1 underneath the 20 and notice it's a whole number, right? It's on top being multiplied to that fraction. Then it's going to reduce with whatever's in the denominator. So 4 goes in itself once and goes into 25 times. Well, this is just 1, so it stays 20. 5 goes in itself once and goes into 24 times. So now I have 5 times that 3x minus 20 times that 1 is equal to 7 times 4. 5 times 3 is 15x. And then we just got negative 20 is equal to 4 times 4, or 4 times 7 is 28. So now I can start solving for x. So what I need to do is I need to add the 20. Since it's a negative, I'm going to add it to both sides. So that gives me 15x is equal to 28 plus 20 is 48. Right? And now let's divide by that 15. Come on. Trying to change it to, there we go. Because I want a positive 1 coefficient on x. So now I got x is equal to 48 divided by 15. And we always reduce in mathematics. If you can reduce, simplify, always. You don't want to leave it just in that format. And this actually reduces by 3. And it gives me 16 15ths. Or excuse me, 16 fives. Okay. So this would be my solution for it. Yep, and there you go. So next they want to know, is it a true solution? See it? They say check your work. They want to know, just because you got x equals that 16/5 doesn't mean it's a true solution. So what I'm going to do is take this original equation here, that 3/4 x minus that 1. We want to see, does it equal, what was that, 7? That thing cut it off, 7/5. If it does, then that means my x equals this is true. Again, just because you get a solution don't mean it's a true solution. So let's plug this in. I'm trying to see if it equals the 7/5. All right. Well, I noticed that I have a 4 in the denominator here. And I know it goes in itself once. And I know it goes into 16 4 times. So reduce if you can. Now I have 3 times that 4 over 5 times 1 minus 1. Well, 3 times 4 is 12 over 5 minus 1. Now, in order to solve this, I need a least common denominator, and I know that 1 is seen as over 1, and the common denominator is 5. So let's multiply both of these by 5. So now I have the 5's reduced, and I got 12 minus 5 is equal to 7, right? Now, I want you to realize that we multiplied this side. Hang on. Come on. There we go. We multiplied this side here, if my highlighter will work. There we go. By the 5, right? This side here of the equal sign. And remember, whatever you do to one side, you have to do to the other. So I really need to do this side. Or, because I mean, I can't just do it to part. Or I could have said, oh, well, let's leave it in fraction form and let's multiply it by 5 over 5. And it would, okay, we would have had to do extra work. But remember, what we do to one side, we must do to the other. So we yielded 7. So let me come up. We yielded 7 over here, but we have to multiply this 5 by 5. And it gives me 7. So check, this is a true solution. Because I was just working on that one side for a little bit. Remember, if I changed it, I have to do it to the same. So we did it. Yay. And again, you could have done, we could have said, we could have done it another way. And that's what they did down there, guys. We could have said, oh, least common denominator is 5. And this one here has the 5. So I'm not changing it, but I'm going to change this one. So if I did that, I would have had 12 over 5 and 5 over 5, which would have gave me 5 over 6. So we would have said 7/5 is equal to 7/5. So there's 2 ways to look at this. Okay. You pick the one that you like. All right. We have special cases here. It says solve for this one. I apologize. My screen here cut off, or it didn't download everything on this example. So if you got the original form PowerPoints, double check to make sure it downloaded to yours. If not, this is what we're going to have. So we're going to work with this part here. So now we have, oh, no, let me erase this. We have this. Okay, so I needed to add this 24x to both sides. So if I added the 24x to both sides, I apologize. I wish it would have downloaded all of this. I'm trying to decipher where it's going. So let's just work with this. Let's say it's 24x plus that 7 and it was equal to 17 minus 24x. Let's just say that was like that. Let's say that was the original. So what do I have here? Well, if I was to move the x's to one side, I always like to move them to the left, and the constants on the right. So if I was to take this 24x here and it was negative, I'm going to add it. I'm going to come over here and add it. This went to 0 here. Oh, it went to 0 here. We have no variable term, and I'm going to bring down what's left. And we're going to look at it. We're going to say, oh, wait a minute. 7 does not equal 17. And the correct notation, my pen got a little carried away. This here means does not equal. You put a line through the equal sign. It means does not equal. So this is not equal. So there is no solution here. We have no solution at all. We don't even have a variable term to consider. All right. So if you want to take a moment and you can work this one out. So looking at this one here, we have, let's rewrite this. I'm going to rewrite this on a different paper. So we got 3 minus 1/3 x. Maybe this, I should have done that on the other one so it'd be easier to see. Is equal to the negative 1/3 x. All right. And I believe this was going to be plus the 3. Yeah. Okay. Let's. All right. Well, looking at this, would you agree that both sides equals each other? I got a positive 3 and a positive 3. I got negative 1/3 x, negative 1/3 x, and separated by the equal, right? So I'm going to say this side is equal to that side. However, let's just do some math work. If I was to say, let's move this 1/3 x to this other side by adding it, because I need it to go to 0 on this one side, it caused it to go to 0 here. Leaves me with 3 equals 3. This here is, and you could have subtracted 3's from both sides. You could have ended up with this. You could have stopped here. You could have stopped at the beginning. So both sides are equal. However, there is no variable term showing. There's infinite many solutions here. So no matter what I plug in, I'm going to yield both sides out equal to each other. So it's infinite many solutions. Okay. So it's all real numbers. Okay, applications using linear models. Mathematical techniques are used to answer questions arising from real number solutions. Linear equation functions models many of these solutions or situations, excuse me. Okay, so these here, just take a minute to pause this, write this down, read it. You need to familiarize yourself with problem solutions. If the problem is presented in words, this means to read carefully. So what I encourage you to do, if you can label the information you're getting out of the application problem, or if you can draw a picture, make a diagram, make tables, whatever it is, and then go to the underlying question. What is it asking for? And highlight it, pull it out. This is what it's asking for, and then go back to the application problem and reread it again and pull the information from what you've gathered that's relevant to the question, and then solve. Sometimes application problems can be overwhelming. And then at the very end, once you determine what your answer is, you're going to go back and say, does this make sense? Can I check my work, check to make sure it's correct? And then, application problems, you should always make a statement and state it clearly that whoever's reading your material will understand what that number actually represents in the application problem. So motion formula, please write this down. Distance equals rate times time. So here we go. We have Delta Airlines fleet includes B737/800s, each with a cruising speed of 517 miles per hour, and SAAB 340Bs, each at a cruising speed of 290 miles per hour. So this is just a source pulled from Delta Airlines. Suppose that the SSA-B takes off and travels at its cruising speed. 1 hour later, the B737/800 takes off and follows the same route. Traveling at its cruising speed, how long will it take for this B737 to overtake the SAA-B? So here in this one here, it would be so encourageable to actually draw this one out. And as you see in this diagram, it drew it out for you. It's a really great looking drawing here. So we have our B737 and we have our SAA-B here. So we have this 517 miles per hour and we have T hours. So our rate was the miles per hour. Then we have the 290 miles per hour for the SSA-B. So it said that the SSA-B took off an hour ahead. So we're going to add 1 hour to it, right? And then D is going to equal my distance in miles. So we have two equations, right? So what I have here, let's just rewrite it. It said D equals R times T. So in this first one here, we would have D is equal to 517 times T. And then this one here would be D equals 290 times 1, or T plus 1. T plus 1. Okay. So now we got that. We can come out here and you can set up this table like this if it helps you. I'd encourage you, whatever works for you. So we have two equations and we're going to set them equal to each other. So I'm going to get my other sheet of paper and I'm going to set them equal to each other and solve. So I'll give you a second to write that down as well. And get my paper. So it's 517. And scroll down. All right. So I got 517T is equal to 290 times T, because I'm going to distribute this, plus the 290. Let's subtract the 290 from both sides, because I wanted to get the T on the left-hand side. And then, so I have what? 517 minus the 290. That gives me 227. T is equal to 290. Let's divide by the 227. So we want a coefficient of positive 1 on T. Whoops, we don't want to carry the T with us though. Don't do that. That should be a 7. Those reduce. Leaves me with 1 times T. So now I got T is equal to, so let's divide it. 290 divided by 227. Gives me, and I'm going to put approximation sign here because it's going to give me a decimal number. We need to see how it wants us to round. So this gives us T time. And let's see how it wants us to round. I didn't see where it asked. Nearest hundreds is what it rounded to. So let's go back and round it to. Oops. All right. To round to the nearest hundreds, I know this is the hundreds place. I'm going to look behind it. I'm going to ask myself, is this equal to or greater than 5? It's just a yes or no. And our answer is yes, because it is greater. All it has to be is yes to at least part of it. So that means I'm going to add 1 here. So I got 1.28 hours. Okay, so that tells me the time it took for the, let's see which one it actually wanted to solve for, because we could state what it is for both. Okay, the B737. If I wanted to know what it was for hours on the SSA, or excuse me, let me say this right, SAA-B, I would add 1 to this here, and this would tell me that one. That would be 2.28 hours for it, and then the B 737 was 1.28 hours. Okay, now simple interest formula. Using a simple interest formula, I got I is equal to the principal times the rate times time. The rate is in percentage, but you always take it out a percent. To undo percent, you're going to divide by 100%, or shortcut, move decimal 2 places in this direction. Okay, so let's do a simple interest. The student's loans total 28,000. One loan is 5% simple interest and the other is 3% interest after 1 year. So both of them is after 1 year. He owes 1,040. I was going to say 1040, but $1,040 in interest. What is the amount each loan? So again, the formula was let's go back. Get the formula. I equals, yes, PRT. Now we want to figure out how much interest it is that they actually paid. He said it owes this much in interest. We want to know what is the amount of each loan. Okay. So we know that R for the first one is 5%, which is, if we was to divide it by 100 or move the decimal 2 places in instruction, we get this here. The second one, R is equal to 3%, which is 0.03. We know that T is equal to 1, T is equal to 1. And I wanted to look at one thing because it said that the student loan was 28. Oh, it's got 2 student loans and they're 28,000. Yeah, that's what I thought they was doing. They set it up. I like the table. It's nice. I was going to set it up like that, but I wasn't 100% if that was the example that they used. So this will work out great. So they use the X is equal to the unknown. So they said, let this equal X. So when they set it up on the table, as y'all can see right here, and I like this table, so we're going to use it. They said that X was what he borrowed. The 5% again was the first one that they checked out in the application problem. And then this was the second. We converted those to decimals. We let it be that. But if you notice on the 3%, it said that 28,000 minus that is because he had 2 loans. You notice at the beginning, it said there was 2 loans. So one loan at the beginning was going to be X, and it's going to be X times this, and then for 1 year. And then we're going to say the 28,000 minus X because they had 2 loans. So we're going to end up with this equation right here. This is the total amount of the loan, and this is the total amount of interest. So let's set this up. We're going to translate it. We're going to take it and set it equal. So what I'm going to do is I'm going to say, oh, and then because this is total, this is the equal sign. That may help you. This is my equal sign. So I'm going to take these 2 and add them together and set it equal to that 1,000. And this is what they get. And it may be easier if I do this on a separate paper. So we got 0. Let me write this down. 0.05x plus the 0.03 times 28,000 minus x equals this. So let's distribute this. Times at 28. And you could skip this step and actually just multiply it. Okay, so I got 0.03 times that 28,000, which is 840. And you could have put the X's together in this step here too, but I just did the extra step. So these two are on the same side, the equal sign. So I'm just going to say 0.05 minus that 0.03, which gives me what? 0.02. X plus the 840 is equal to 1040. Let's subtract the 840 from both sides because I want it on the other side. So I got 1040 minus the 840, which is 200, right? And now let's divide by the 0.02 on each side, because I want a positive one coefficient on X. And that gives me 10,000. Okay, so the 5% interest would be the 10,000 if I was to come back and put it in the table. Now I wanted to figure out what is the other student loan. As you see here, they've shown you this. So X is that. And then if I wanted to figure out the other one, I would say, oh, okay, it's for the 3%. I'm going to subtract that 10,000. And that's going to give me 18,000. So I have two loans, one for 10,000 and one for 18,000. So that's what it's showing you. And then you could check your work by plugging it in, checking to see if it gives you a solution. All right. Now let's talk about the zeros of linear functions. An input C of a function f is called a zero of the function if the output for the function is 0. When the input is C, that is, C is a zero of f, we get f of C instead of x is equal to 0. And we're going to use the same method we've been solving. And we're going to solve for it. All right, so I'm going to find the zeros of this. So what I need to do is acknowledge that 5 of x minus 9. I need to acknowledge this is going to be 0. So I'm going to set it equal to 0 and solve. I add the 9 to both sides. And then I have 5x is equal to 9 and divide by the 5. Now I got x is equal to 9/5, which is the same as 1.8. Okay. And that's what we're doing. You're looking for the intercepts, basically, is all that's saying. You can solve for the intercepts, and that will give you the real zeros. You can use your calculator, and you can find them. Again, your real zeros will be wherever it crosses the x-axis and the y-axis. Those are my intercepts. Thank you.